Have you ever looked at a bridge or an older building and wondered, how do engineers keep these things standing strong, especially when they start showing their age or take a real beating?
It's a great question. Structures need maintenance, sometimes significant upgrades.
Exactly. So today, we're doing a deep dive into that very topic,
Yeah.
how we can make our concrete structures stronger, safer.
Mhm.
We're focusing on a really interesting study looking at reinforced concrete corbels.
Ah, yes, corbels.
Yeah.
Crucial little elements.
Right, and how this cutting-edge material, carbon fiber, reinforced polymer CFRP sheets, how that's being used to basically optimize them, especially after they've been damaged.
It's a fascinating application of advanced materials in structural repairs.
So our mission here is to pull out the key insights from this research, give you a shortcut to understanding where structural repair might be headed.
Sounds good. Let's get into it.
Okay, so let's unpack the basics first. What exactly is a concrete corbel for listeners who might not know?
Sure. Think of it as a short, stout bracket, almost like a ledge sticking out from a column.
Okay.
Its main job is to support heavy loads, like from a beam, and transfer that load safely into the column.
And they're sort of distinctive looking, right? Quite chunky.
Exactly. Engineers define them by their shear span to effective depth ratio, the add ratio. It's usually less than 1.
Meaning they're deeper than they are long, essentially.
Pretty much. And because they're so stout, they behave differently than a long, slender beam. They don't primarily bend.
Ah, okay. So how do they behave then?
More like a deep beam, or even sort of like a basic truss. They're mainly resisting shear forces that direct slicing action.
Gotcha.
And because of that geometry, that low add ratio, shear is really what governs their strength, much more than bending stress.
And you said they're critical elements.
Absolutely. They're the transfer point for significant loads in many structures. Think bridges, precast building frames.
But that design also makes them vulnerable.
It does. They can fail in a few ways. Diagonal splitting is common, shear sliding, bearing failure right under the load. But shear capacity is often the limiting factor.
Okay, so that's where new materials might come in handy.
Precisely. This brings us to materials like fiber-reinforced polymer, or FRP composites.
Right.
These are being used more and more as external reinforcements. Basically, you apply them to the outside of an existing structure to boost its strength or repair damage.
So what are they made of?
Well, at their core, their reinforcing fibers could be carbon, glass, aramid embedded within a polymer matrix, like an epoxy resin.
Like threads held in glue.
Kind of, yeah, but super high-strength threads. And they can be formed into different shapes, bars, plates, and in this case, sheets.
And I gather they have some real plus points compared to, say, adding more steel.
Oh, definitely. The advantages are pretty compelling.
Such as?
Well, first off, they're lightweight, much lower specific weight than steel, so you're not adding significant dead load to the structure.
That's a big deal.
Huge. Also, lower thermal expansion, they're easier to handle and apply on site, often non-magnetic.
And corrosion resistance must be a major one, right? Compared to steel rebar.
Absolutely crucial. FRP doesn't rust, it's chemically stable, has great fatigue performance, and importantly, it generally boasts higher tensile strength and stiffness modulus of elasticity than the concrete itself.
So stronger and stiffer, in simple terms.
In tension, yes, very much so.
Okay, so FRP is the general category, but the study focused specifically on carbon fiber reinforced polymer, CFRP. What makes that special?
Right, CFRP is often considered the premium option within the FRP family.
Why is that?
Well, carbon fibers generally have a higher Young's modulus, that measure of stiffness, compared to glass or aramid fibers. They're incredibly strong and stiff for their weight.
Okay.
Plus, CFRP tends to have excellent durability, long lifespan, good fatigue resistance, and it holds up well even in the alkaline environment of concrete.
Which makes it good for concrete repair specifically.
Exactly. It's particularly relevant for things like precast concrete connections or structures in seismic zones. You need strength, some flexibility in the system, and the ability to dissipate energy during an earthquake. CFRP systems can help provide that.
Sounds almost too good to be true. Other downsides? Challenges?
Oh, for sure. Nothing's perfect. CFRP itself is a brittle material that doesn't stretch much before it breaks.
Ah, okay.
Application can be tricky too. It's sensitive to the surface condition, needs to be dry, and high temperatures during curing can be an issue. And yes, cost is often higher than traditional methods or other FRPs.
Right, always a trade-off.
Yeah.
Okay, so let's dive into the experiment itself. What did they actually test?
So the researchers looked at 9 reinforced concrete corbel specimens. They were carefully constructed a central column bit with two corbels sticking out, one on each side.
Like a T-shape.
Sort of, yeah.
Yeah.
A short column, 200 by 200 millimeters, 800 millimeters high, and the corbels cantilevered out 300 millimeters. Standard concrete, reinforced with typical deformed steel bars, the kind you'd find in real construction.
Okay, so realistic models. And how did they use the CFRP?
They tested two main strengthening configurations using CFRP sheets. Configuration 1 was full-side wrapping covering almost the entire side face of the corbel.
Okay, total coverage.
And Configuration 2 was strip wrapping. Here, they applied CFRP strips only over the areas where cracks were expected or had already formed in the damaged specimen.
More targeted.
Exactly. And before strengthening, the specimens were grouped. One was the control-tested straight to failure, no CFRP.
The baseline.
Right. The others were pre-damaged to specific levels, 50%, 60%, or 70% of the control specimen's ultimate load capacity.
So they deliberately broke them a bit first.
Essentially, yes. They loaded them until they reached that target damage level, then unloaded them, then applied the CFRP strengthening, and finally reloaded them to failure.
How did they apply the load?
With hydraulic jacks, applying symmetrical forces down onto steel plates placed on the corbels, mimicking how beams would load them.
Gotcha. And what were they measuring? What defined performance?
Key things: ultimate load capacity, the maximum load before failure; mid-span deflection, how much they bent; stiffness, the relationship between load and deflection.
Oh, okay.
They also observed how cracks formed and spread, and importantly, the final failure mode, how the specimen ultimately failed.
And the application of the CFRP itself, that had to be done carefully.
Oh, very. The procedure involved mechanical grinding of the concrete surface to ensure a good, clean bond. Then they applied a specific epoxy adhesive and carefully placed the CFRP sheets. The bond is critical.
Right, makes sense. Okay, so the results. What do they find? Let's start with the ultimate load. How much weight could they handle?
This is where it gets interesting. The undamaged corbels that were strengthened with CFRP, they showed a really significant boost.
How significant?
A 19.72% increase in ultimate load compared to the control specimen. That's going from 710 kilonewtons for the control up to 850 kN for the strengthened ones.
Wow, nearly 20% stronger just by adding the CFRP wrap.
Exactly. And 850 kilonewtons, that's roughly the weight of, what, over 85 medium cars? It's a substantial increase.
Yeah. That really puts it in perspective.
Yeah.
Okay, what about the ones that were already damaged before being strengthened?
That comparison is fascinating, too. And here, the type of wrapping mattered. The side-wrapped specimens configuration 1 consistently showed greater load improvements than the strip-wrapped ones.
Ah, okay. Example.
Sure. For the specimens damaged to 50%, the side-wrapped one, RCS51, saw a 13.73% load increase after strengthening.
Pretty good.
Yeah, but the strip-wrapped one at the same damage level, RCST52, only got a 9.86% improvement.
So side wrapping was clearly better for restoring strength in damaged corbels.
It seems so. The thinking is that the fuller coverage of side wrapping does a better job resisting those diagonal shear stresses that are so critical in corbels. It provides more comprehensive support.
Okay, so more load capacity. What about stiffness? Did they get less bendy?
Yes, significantly stiffer too, and stiffness and deflection are obviously related.
Right, less deflection under the same load if it's stiffer.
Precisely. The side-wrapped, undamaged specimen, SCS-01, showed a massive 52.15% increase in stiffness compared to the control.
Over 50% stiffer. Wow.
And consequently, its displacement, its deflection at peak load, was 21.3% lower than the control.
That's a big difference in how much it would sag.
Definitely. Even the strip-wrapped undamaged one did well, 47.4% stiffer and about 18.7% less displacement. So both methods significantly stiffened the undamaged corbel.
But what about the damaged ones? Did stiffness improve there too?
It did, but there was a clear trend. As the level of pre-damage increased, the stiffness improvement decreased.
Makes sense intuitively.
Yeah. For instance, side-wrapped corbels damaged at 50% saw about a 38% stiffness increase. But at 70% damage, that improvement dropped to around 24%.
Still an improvement, but less dramatic.
Right. And interestingly, across all damage levels, the side wrapping consistently resulted in slightly higher stiffness, about 3 to 5% more than the strip wrapping.
So side wrapping seems better for controlling deformation too.
That's what the data indicates, yes. Superior deformation control.
Okay, so we have increased load capacity, increased stiffness, especially with side racking.
Yeah.
But there's a but coming, isn't there? You mentioned the 70% damage level.
Yes. This is a really crucial finding. While CFRP helped at 50% and 60% damage, the specimens pre-damage to 70% showed very little improvement in their ultimate load capacity after strengthening.
How little?
For the strip-wrapped one at 70% damage, the increase was only 0.51%, basically negligible.
Wow. Almost no benefit at that point.
Pretty much. It really suggests there's a critical damage threshold.
So it raises the question, when is it just too late for effective CFRP repair?
Exactly. This data strongly implies that CFRP repairs are much less effective if the structure is already severely damaged. The best results, the most bang for your buck, seem to come when it's applied before damage reaches that 50% level.
Which really underlines the need for monitoring structures, doesn't it? Catching damage early.
Absolutely. Proactive structural health monitoring and timely intervention. It's like preventative medicine for buildings and bridges, much better than waiting for a critical failure.
Okay, now here's something that really caught my eye. The failure mode. You said all the reinforced corbels failed because the concrete cover came off, not because the CFRP itself broke.
That's correct. It wasn't CFRP rupture, it was debonding or delamination initiated by the failure of the concrete underneath the CFRP.
What does that tell us?
Two main things. One, it highlights just how critical that bond is. Surface preparation, the right adhesive, proper application, it's absolutely paramount for transferring the stress effectively from the concrete to the CFRP. The system is only as good as its weakest link, which in this case was the concrete cover or the bond interface.
Okay, makes sense. What's the second thing?
The second thing is actually quite positive and maybe a bit counterintuitive. Even though failure initiated in the concrete, the way they failed was different.
How so?
The CFRP strengthened specimens showed more controlled, localized failures, and importantly, they exhibited enhanced ductility and energy dissipation.
Wait a minute. Earlier you said CFRP is a brittle material. How does adding a brittle material make the whole thing more ductile? That sounds contradictory.
That's an excellent question. It seems paradoxical, doesn't it?
Yeah.
The CFRP material itself is brittle. It won't stretch much.
Right.
But when it's bonded effectively to the concrete, it changes the system's behavior. It acts like a confining wrap or reinforcement.
Okay. How does that help ductility?
Well, as the concrete starts to crack or crush internally, or even as the internal steel reinforcement starts to yield, the external CFRP layer holds everything together. It prevents sudden, catastrophic failure modes like explosive splitting.
Ah, so it contains the damage.
Exactly. It forces the failure to be more gradual. The system can deform more, absorb more energy before it ultimately loses its load-carrying capacity. Even after the peak load is reached, the load decreases more slowly rather than dropping off suddenly.
So it gives warning. A less brittle failure for the entire corbel.
Precisely. It transforms a potentially brittle shear failure into a more ductile, controlled failure mechanism. And that's a huge safety benefit, even if the CFRP itself doesn't stretch much.
That's a really key insight. Enhanced system ductility from a brittle material.
Okay. And did the researchers see any signs during the tests that failure was approaching? Any warning indicators?
They did notice something interesting in the load deflection curves. There was often a distinct knee or change in slope at about 85% of the peak load.
A knee in the graph. What did that signify?
They interpreted this as the onset of CFRP debonding. The point where the adhesive starts to let go or microcracking really picks up pace near the bond line?
So that knee could be like an early warning signal in a real structure.
Potentially, yes. For engineers monitoring structures, observing that kind of behavior change under load could be a valuable diagnostic tool. It signals that the strengthening system is being significantly stressed and approaching its limit.
Fascinating. Okay, let's connect all this back to the listener. What does this research mean for, people who aren't structural engineers but live and work in these buildings? Why should they care?
Well, fundamentally, it's about safety and resilience. This research gives engineers better tools and data.
How so? It provides quantifiable evidence of how CFRP can make critical structural elements, like these shear-prone corbels, behave in a safer manner, making them less brittle, more ductile.
Right, that gradual failure thing.
Exactly. It also informs crucial decisions about when to intervene. That 50% damage threshold is a practical guideline. Repairing early is far more effective.
So better timing for repairs.
Yes. And it helps refine how to apply the strengthening, showing that side wrapping offers more benefits in these cases. All this leads to safer structures that fail more predictably if overloaded. And that contributes to more resilient infrastructure overall.
Especially in places prone to earthquakes, I imagine. where ductility is paramount.
Absolutely critical in seismic zones. You need structures that can absorb energy into form without sudden collapse. CFRP strengthening, done right, can contribute significantly to that.
Okay, so let's quickly summarize the big takeaways from our deep dive today.
Sure. I'd say first, CFRP strengthening significantly increases both load capacity and stiffness of concrete corbels, whether undamaged or moderately damaged.
And side wrapping generally outperforms strip wrapping, especially for damaged elements.
Correct. Second, there appears to be a critical damage threshold, probably around 50% or maybe a bit higher, beyond which CFRP repairs offer much less benefit in terms of strength gain. Early intervention is key.
Got it. And third,
Perhaps the most important safety insight. CFRP confinement changes the failure mode, enhancing the system's ductility and energy absorption. It leads to more gradual, controlled failures, even though the CFRP material itself is brittle.
and that debonding knee provides a potential warning sign.
A useful diagnostic indicator.
So looking ahead, where does this research point? What's next?
Well, if we connect this to the bigger picture, it opens up several avenues. Exploring hybrid techniques, maybe combining CFRP with other materials or methods.
Okay.
Developing even better, more durable bonding agents is crucial given that debonding was the failure trigger here.
Right, improving that weak link.
Exactly. And more research is needed on long-term performance, how these repairs hold up over decades under real-world environmental conditions, freeze-thaw cycles, and repeated loading, like traffic on a bridge.
Makes sense. Durability is key.
And ultimately, all this work feeds into developing better standardized design guidelines. So engineers everywhere can confidently and effectively use CFRP for strengthening, making it a more routine part of structural engineering practice.
It really shows how innovation is constantly happening, often unseen, to keep our structures safe.
It does. Continuous improvement based on research and testing.
So here's a final thought for you, our listener. As you go about your day, maybe take a closer look at the buildings, the bridges, the infrastructure around you. Consider the hidden engineering, the ongoing research like this that works constantly to make our built world stronger and safer. And maybe wonder, what other advanced materials might be quietly revolutionizing the structures we rely on every single day?